Yeah, then we will start from the first question. In the first question, it is asked that the entropy of an isolated system always dash and becomes dash at state of the equilibrium. Now first we will understand, we have to define what is an isolated system is. So for an isolated and what is an isolated system is. Now an isolated system is defined by a thermodynamic system. Let me use a question 1. So the isolated system
Are you writing, sir?
yeah.
Oh, I am not able to see.
Acha, ये क्या you are not able to see?
Yes, sir.
Okay.
We just seeing your just cursor.
Okay, but you are not seen anything hidden. Okay.
पूरा ब्लैक ब्लैक दिख रहा था.
Okay. Allow to scan. अच्छा, आप देख पा रहे हो स्क्रीन मेरा पूरा?
हाँ, अभी आपका स्क्रीन देख पा रहे हैं. जब आपका स्लाइड ऑन होता है तो आप म्यूट में हो जाते हैं.
अच्छा.
और जब अभी दोनों हो रहा था तो स्लाइड पे जो आप लिख रहे थे वो नहीं दिख रहा था.
आप देख पा रहे हो स्लाइड मेरा?
हाँ, यस, आइसोलेटेड सिस्टम.
हाँ, देख पा रहे हो, ठीक है. चलो, तो what is isolated system? So first we will define the isolated system. So an isolated system in thermodynamic sense, and whatever we will did here, it is in the thermodynamic sense. So in thermodynamic sense, the isolated system is a thermodynamic system. Can you see now? Now you can see, right? A thermodynamic system. A thermodynamic system enclosed by, enclosed means its boundaries, enclosed means since it is a system, so it is enclosed by some walls. If it is a 3-dimensional system, then there are 6 walls has to be needed to enclose the system. Now this, for isolated system, this wall has to follow some property. What property it is? The property will be, the wall will be, one is immovable, it cannot be moved, immovable, immovable. Okay, let me write it again. Immovable. Second will be, immovable means the wall cannot move, it is fixed in the positions. And the second is isolated, second is insulated. Insulated means no energy can pass through these walls. And third is impermeable. Impermeable means no particle can go through these walls. So if that 3 properties of the walls has, then the system will be called a thermodynamic system. Now as in the questions, it is asked that the entropy of an isolated system, so that means if it is isolated, that means no heat can flow into the system. From the first law of thermodynamics, we know that dq equal to du plus p dv. Du is the change in the internal energy, and p is if the pressure is applied on the system, and dv is the change in the volume. Then dq is the total heat is required that we have to give to the system or we have to extract from the system. So if it is immovable, that means whatever pressure will apply, there will be no movement at all. So that means dv is 0, that means this term is actually 0. Since no isolated, so no energy can go through, so this dq is also 0. And if there is some chemical potential also, since that is impermeable, this dN the number of particles go through this changing in that system is also 0. That means the all term is 0. That means the no change of heat or no change of heat, and this first law can be expressed if we use the second law, and this first law can be expressed in terms of TdS in equal to du plus PdV. That means if the system is in the true sense isolated, there will be TdS is equal to 0. That means ds will be 0. That means entropy cannot be changed in an isolated system. But this question has a typo. This entropy is, this system is not the true isolated system. The question is meant by the isolated in sense of thermodynamic sense, in thermodynamic sense, thermodynamically isolated. What it means? Thermodynamically isolated means it is the walls will be impermeable and the immovable and the and this is that insulated. That means no heat can be go through these walls and the no particle can be exchanged. Now if these two happens from this, that means if these two also, the wall has these two property, but if it has not this property, that the wall can movable, then this PdV can be changed. That means suppose a system which is, suppose that there is a system which is system of gas which actually expand, since there is a pressure applied here, there is a pressure, some mg is a mass, some mg is there, so there will be some pressure through this piston, and suppose that this gas is expanding. If this gas is expanding, that means this PdV will be some positive. Now the gas will be expand to that limit where its entropy will be maximized. If it is a thermodynamically insulated system, that means it's, if it is thermodynamically entropy system, and that means it is a system isolated by immovable walls. That means the wall can move but no heat can exchange through the system, exchange between the system and surroundings. Now if in this system, the system can go towards the equilibrium position, and equilibrium, it will reach the equilibrium position by changing its volume, and in this process the entropy will be increases. Then if it is an thermodynamic system, then we can know that this isolated system, the entropy will always increase. This will be increases and becomes at the end of the day maximum, at the maximum. This means from here, that means this gas will expand toward a volume where its entropy will be maximized. So that is that. So in the first case, if the system, the question is actually has an error, it is not isolated system, it is meant here that it is an thermodynamically isolated system. So let me check one thing. Okay. Yeah. So that's that. So the first question, we have solved the first question. That means if the system is an thermodynamically isolated system, then the system always increases, the entropy of the system will always increases and reaches to a maximum at the state of equilibrium. So, and now we will go toward the second question. Which of the following statement is true? A given macro state typically corresponds to a huge number of microstate. Is it true? Yeah, it is true, because a microstate is macrostate is content. A microstate is the cross-graining picture of this state. Macrostate means a cross-graining picture of its microstate. Now its microstate can be different, but the macrostate can be same. So a macrostate typically corresponds to huge number of microstate. It is true. It is true. That means physically it means that if I have a box of gas, if remains its pressure, volume and temperature constant, that means it's a given macro state. But in the microscopic level, the particle can be erratically change its position momentum. That means infinite number of microstate possible in principle for a given macrostate. So the first statement is true. Now a given state always has exactly one microstate. It is not true. It is not contain. It can happen. So one macrostate with only one microstate, but it is not true for every case. So that statement, second, it is true. Then the statement a given macrostate always has a only one microstate, it is not true. It is actually false. But the vice versa is true, that a macrostate can contain only one microstate, then it is legitimate to call this macrostate a macrostate. But it is not always true, as in case of the gas. This if I remains constant its pressure, temperature, volume, inside its microscopic constituents can change, and that means this statement is not true always. Now second is the entropy is a function of microstate of the system, right? Since as in the course the entropy is defined as the Boltzmann defined the entropy, in sense the entropy will proportional to the log of total number of microstate. So that means entropy is always a function of microstate. Now it can be seen in other ways also. Suppose that entropy is a function of microstate, how it is. Now what the entropy measures, actually in entropy actually measures the disorder, right? So disorder, what the disorder means? Disorder means that what is the information of the system is lost. Disorder means I don't have any information about the system. If it is ordered, then I can say that the system is that. But if that system possesses no information, that means I will call the system is in disorder state. So what is the meaning of disorder? That means it can be possess a many number of microstate. When the microstate of a given macrostate will be large, then I cannot exactly pin down what the system's constitution is actually. That actually, in other words, when that means that is the disorder, I cannot exactly pinpoint what is the status of this macrostate. That actually physically tells us that entropy, which is actually measure of disorder, should actually proportional to should be a function of this total number of microstate. As microstate increases, the information is by looking a particular picture of this macrostate, I can tell that what is the system is. So that means the information is lost. That means entropy should also always a function of microstates. So this is also a true statement. Now the third, different microstate always corresponds to different macrostate. Different microstates always corresponds to different macrostate. No, it's not always. Different microstate not always corresponds to different macrostate. It is not true. As in our previous example, gas example, in a given pressure, temperature, volume, there will be very huge number of microstate. The huge possible ways to there is a possible configuration of this particles momentum and position. So that means there will be different microstate, huge number of microstate which actually indicates a single macrostate. So that means it's always not true that different microstate always corresponds to different macrostate. It's actually not true, so it is a false statement. So yeah, is it clear to you? Can you hear me exactly? Yeah, hello.
Yes, sir.
Oh, okay. If anything is not clear to you, just stop me and ask question, right? Now,
Okay, sir.
so now it is the third question. We'll go toward the third question. Now, from a standard deck card, if you have a hand of 8 cards, 5 of which is black, calculate the entropy. Right. So now we will calculate the entropy in the sense of Boltzmann sense. Now to proceed further, we have to know that there are actually I know 3 notion of entropy. One of them is Boltzmann entropy, which actually this, and the other two are, one is that called Shannon entropy, which actually relates the probability if there is a microstate and the probability of this microstate is P, suppose N, suppose S, so PS. So in terms of probability, we can also define a entropy which is called Shannon entropy, and this is actually Boltzmann entropy. And there are another entropy in dynamical system which is called the Kolmogorov entropy, which actually measures the chaotic behavior of the dynamical system itself. So there are 3 notion of the entropy. Now in some limit it can be shown that these 3 entropies are interrelated. That means Boltzmann entropy, Shannon entropy, and for particular system, means for very specific cases, this Kolmogorov entropy can also be seen, means you can also exactly calculate that this Kolmogorov entropy is actually same as these 2 entropies. Now here, here we have to calculate this entropy. Here entropy means our Boltzmann entropy or Shannon entropy. So here we will calculate the Boltzmann entropy. So for the standard deck cards, if you have 8 cards, 5 of which are black, calculate the entropy. So let's calculate how many possible ways we can take 8 cards, and out of which will be 5 will be black. So let's see that. Now if there are we know that there are 56 numbers of cards. Now from these 56 number of cards, we know that there will be 26 number of black card and 26 numbers of red card. Now the question is that if I take 8 cards at random, then 5 of which are black, that means if I take 8 cards somehow randomly, then what is the probability, it's not the probability, how many ways I can choose such 8 cards where the out of 8 5 will be always black. So let's see that out of 8 5 will be black. That means 3 8 minus 5, actually 3 will be always red. That means 5 will be always black. That means 3 will be always red. That means the number of ways we can take this will be 5. 26 C5 into, and that means at first we have taken the 5 cards, then I have to choose the 3 red cards. How many ways I can choose 3 red cards? Into 26 C3, because if I already choose 5 black cards, then I have to choose 3 red cards. 3 actually red card. How many ways I can choose 3 red card from 26 red card? It will be 26 C3. Now the Boltzmann entropy will be Sn will be some constant. It actually proportional, there will be some constant. It happens to be this constant is actually Boltzmann constant. So this is actually a Boltzmann constant. So the actually we multiply this Boltzmann constant to make it's in the same footing of thermodynamics. So in ln W, which will be Kb into ln 26C5 plus ln 26C3. So if you put the value of kb's and this, you will actually exactly get the number. I am not calculating those number. Now I will see that another way, that's what I am telling you, that the Shannon way of calculating this entropy also. Now in the Shannon case, it is the Boltzmann entropy, actually Boltzmann entropy. Now there is another way, is called Shannon entropy. Shannon entropy. So in Shannon entropy, we need the probabilities. So what is the probability? Out of 8, 5 will be black. That will be out of 5. That will be, what is the probability that I will pick 5 black and 3 simultaneously, 3 red will be, that will be, I will pick the number is 26C5 by I can choose the, okay, it will be, so the probability, what the probability will be, 26 ways, total number is 5 card. No, it's okay, okay. So 26C5 into 26C3, let me rewrite it, it will be clear. Probability will be that it is simply this factor 26C5. Actually this 26C5 means 26 factorial by 26 minus 5 factorial into 5 factorial. So if you put this number, you actually get, this means that is the total number of ways I can pick this combination, that 5 black and 8, and how many ways I can random way I can pick 8 cards out of 52. It's 52C8. So it is the possible number of ways I can pick 8 cards, and out of that 8 cards, what is the probability that my card will be such that the 5 of them will be black and 3 of them will be red, is that. So that means this is the probability of happening this exact event. The out of 8, 5 will be black and 3 will be red. Now that means then the Shannon entropy will be exactly minus Pn log, it is log in the base of natural base, log Pn minus 1 minus Pn ln 1 minus Pn. Now it can be shown that in the thermodynamic limit, that means when my the sample space will be large enough, then these two entropy will be same. I think it is there in the Patria books. So if you, in case exactly you can exactly calculate this, exactly matches to number for a spin system. It is there in the Patria's books. If you want to check further, you can go there. So now we will move since
Patria book in the first exercise.
Patria books,
first exercise of Patriya book.
Fast exercise, no, fast exercise not. It's it's where it is actually there in the spin, with the spin systems, where in the chapter I think it may be 5 or 4. I actually forget the exact
Oh,
chapter.
because first is the thermodynamic relation and just a consequence of the
Okay, maybe
thermodynamics.
okay, then maybe it is in the first chapter, so it is there in
Okay,
first.
yeah, I will check.
So now let's go to the fourth problem. The fourth problem is that in the same line, that Alice has 3 black and 3 red cards in hand, picked from a standard deck of 552, while Bob has 4 black and 2 red cards also from a standard decks of cards whose hands of the cards are the higher entropy. Now here every sense the entropy means the Boltzmann entropy, but you can always do the same problem with the Shannon entropy, and you will reach to reach towards the same conclusion. Now let me show you that it's basically the same basic, because this, if you calculate this, basically you will get this plus some factor, plus some constant factor, and that in that way this essence of these two entropies will be same. Okay, so now we'll calculate the entropy of Alice has 3 black and 3 red cards in hand from a standard cards of 52 cards, and Bob has a 4 black and 2 red cards. Okay, that means it's 6 and 6. Okay, so that means again the Alice has 3 red and 2 black card. That means what is the possible number of ways I can choose simultaneously 3 red card and 2 black card? That will be 26 C3 into 26 C2. So it will be, it's the total number of microstate of the Alice, means that many ways Alice can pick simultaneously 3 red cards and 2 black cards. So it will be 26 into 26 factorial by 26 minus 3 factorial into 26 factorial by 26 minus 2 factorial into 2 factorial. So it will be 26 into 25 and 2 24, because 23 factorial 24, and it will be 3 into 2, so this will be 4 into 26 into 25, because 25, because the 24 is cancel out, and 2 factorials means 26 means 13. Okay, 26, maybe 26 will be there, so this will be 2. So that means it actually be 26 into 25 its square into 2. And what is the possible microstate of Bob's actually simultaneously Bob's hand, Bob's actually simultaneously pick 4 red card, simultaneously 4 red card and 2 black. So okay, so what will be, it will be microstates of Bob, it will be 26 C4 into 26 C2, right? So that means 26 factorial by 26 minus 4 factorial, 26 minus 4 factorial into 4 factorial into 26 factorial by 26 minus 2 factorial into 2 factorial. So it will be 26 into 25 into 24 into 23 into 22 factorial by 22 factorial into 4 factorial. So it will be cut, and similarly 26, it is it is not 3, it is actually 3, so maybe I'm wrong, so it is 3 factorial, so it will be 6, it will be 24, it will be 4, so this will be, so this will be actually 24, 4 actually 25 is a 4 square. Now here it is 26 factorial by 25, because 24 factorial is 2, so 2, okay, so there will be 2 factorial, 2 factorial means actually 2, so that's there. So this is actually 26 into 25 its square into, it is 24 by 4 factorial, actually 4 factorial means 4 is 4 into 3 into 2, which is actually 24, so 24, so and 23, okay, 23 by 2, so that's that, 23 by 2. So now if we compare these two numbers, that omega, that means if I write it, that 26 into 25 it is actually omega a by 16, right, omega a by 16, so it is actually omega a by 16 into 23 by 2. So this is actually, that means omega b by omega a is 23 by 32, which is actually 32, which is less than 1. That means omega b is less than omega a. That means Bob's entropy is less than the Alice entropy. But in the first place, means apparently it is not means it is good sense, but apparently one can say from this example that since the Alice has 3 black ball and 3 red cards, that means it has some symmetric, some ordering kind of things, so that means it one can think that Alice should have less entropy than the Bobs. Now what it is get, but it is actually otherwise, that not Alice entropy is less than the Bob, but the Bob's entropy is less than the Alice. So it is because actually not because the one can think it is symmetric sense, but it is not actually symmetric sense. It is all about how many ways one can get 6 card, and simultaneously 3 cards out of that 6 will be black and 3 cards out of that will be red, and that's that. So it is nothing about the symmetric situation of the system, but rather that what is the information can I take from these things, what the information can I take from this statement, that out of 3 black and 3 red, it is less informal in a sense, since let me check, it's Alice has a getter in, right, Alice has a getter entropy, that means that Alice has a getter entropy, that means this Alice situation will be less, contain less information, because since this it have same number of black and red balls, it actually contain less information about that structure, about the if I ask that Alice, say what is the thing that you have, it will say that the I, if we just pick one card from its 6 sample, it will be anything black or red, so that means this state will be less contain less information, and this while the Bob has 4 black and 2 red, that means Bob at least can say from his state, if I pick randomly from my 6, it will be more probable that I will get a black card out of it. So that means in that sense that Bob has the greater information from his sample. So that means the Bob has the less in the Bob's microstate is less entropy, and that actually means that Bob's has the higher information. So that's that here that will be that question is whose hand cards has a higher entropy. So that means Ali's hand cards will be the higher entropy. Now the fifth question will be, consider a case where there are 3 steps in a staircase with all equal heights age, and there are 3 different people. These things are actually notice these things, that these peoples are different people. That means we can the peoples are indistinguishable. In a sense, we can give indexes to the peoples which actually uniquely tell that which individual it is. Means we can actually distinguish the which peoples it is. That means you can think about that it has a name, that it's Alice, Bob or something. So that means these 3 individuals are indistinguishable with different people, which has a indistinguishable property, and that there is a where the 3 steps in the staircase. In the staircase there is a 3 step, and which is equal height. Okay, on the staircase with equal heights, how many ways can the potential energy will be 8 Wh? So let us see that. So there will be 3 staircases and 3 indistinguishable individuals. So we will take the A as the first individual, B is the second individual, C is the third individual, and these are the first stair, this is the second stair, this is the third stair. Since the first stair is in the 0th it's ground level, so we can so 6 energy 6. So with how many ways can the potential energy will be 8 omega h, right? So 8 omega h. So first let's see that its height will be h, and since the everyone's weight is W, that means the energy in this potential energy of an individual in this staircase will be WH, and in the second case, since it is upper from the first by an height h, so it will be 2h, so its energy will be 2 omega h, and it is the height upper from another h, so it will be 3 omega h. So 3 omega h. So 3 omega h. So let me write it down that it is 2 omega h and it's 3 omega h. Now how many ways we can put it there? So let it write it there, how many ways we can put it. So first I can put all the individuals A, B, C there, 0, 0 there, means no individual at this step, and we can put A, B but C there, or we can do that A, B, this is 0 but this is C there, so 3 possible. And another way will be I will put A, C, B will be there, 0, and A, C, 0, B will be there, so that way we can put it there. And another things will be I can put A, B, C, right? We can put B, C, A and C, A. So that many ways we can put. Then what is the number? 1, 2, 3, 4 5 6 7 8. So 1 2 3 4 5 6 7 8, and there will be another way I can put it. There is will be 0 0. So many ways I can put them in there. It's actually I show you the 9 possible ways. There will be actually 27 possible ways, because you see that I can put 3 individuals in 3 different individuals in 3 different stair in 3 to the power 3 ways, because for a particular configuration you can see that for a particular configuration, suppose that A B fixed, I can put this configuration 3 ways. In similarly A C fixed, there will be 3. So in this way I can no, I am maybe wrong. So maybe it is actually 3 to the power 3 ways I can put it out here. So there will be 27 possible ways, 27 possible ways by which I can put them. Now the exact question is, how many ways I can put them such that the potential energy will be 8 omega h. So to 8 omega h, I need, there are how many ways? If I put 2 individuals there, so then there will be 6 omega h. Suppose that our configuration will be 2 people there and 1 people here. So first, for total energy 6 omega h, I put 0 individual here and 1 individual here and 2 individual there. So that means this will be 6 I need 8 omega h, right? I need 8 omega h. I need, okay, 5, okay, I'll need 8 omega h, 8 omega h, 8 omega h, 8 omega h. So it will be 8 omega h. So I need 2 individual there, that means 6 omega h. 2 into 3, 6 omega h plus 1, so 2 omega h. So this will be 8 omega h. So this is one possible way. Let's see other possible ways. Now I can put 1 individual everywhere, so then also a possible 1 1 and 1. So h, 2h, 3h. No, it is not possible. It is not possible. So I can put 2 individual there, 2 individual there, so 4, 1 individual there. It is also not possible. So only possible way maybe only this, because if I put 3 individual there, then also 9h, it will not possible. 3 individual there, it is actually 6. There is not 3 individual, 2 individual there, so 2h and 5h. So everyone 1h. No. So it's only one possible ways we can get the potential energy 8 omega h. It's 8 omega h. So only one possible ways we can put 3 different people in such a way that its total potential energy 8 omega h. Let us check again that if I put 1 individual there, so 3 omega h and 3 said 6 omega h, so it will not possible. So actually it is not possible. So only one way we can get 8 omega h. So it will be the maximum potential energy we can get out of this system, that in the 3 step. And no, maximum energy will be 8 omega h, because if I put 3 individual in the highest energy state, then it will be the 3 into 3 omega h will be 9 omega h. So the maximum will be that, and the less it will be 8 omega h. And in the 8 omega h, only one possible ways one can how many is one possible ways that one can get the potential energy 8 omega h. Now in the sixth question, now let go to the sixth question, that for the system as above question, what value the potential energy will have the maximum possible ways of occurrence. So let me check. So this is that. So only one possible ways we can get that. Now for the same system as above question, what value of the potential energy will have the maximum possible ways of occurrence. So which energy will maximally occur? So let's see it. So it's seem that 9 omega is maximum. So if there is a maximum ways, so and this is minimum 0, this is 0, because at the in the minimum energy will be all the individuals remain in the minimum state. All individuals remain in the minimum state. That means if all individuals remain there, so that will be 3 omega h, that will be minimum. That means only one way is possible to get 3 omega h, and only one way also possible to get 9 omega h. And if the entropy has a maximum, it may be remain between these two, because entropy, if the microstate is 1, then the entropy, since we know the entropy is ln of the number of microstate, then that means it is 0 here, and for 9 omega is also only 1 possible, so it is also 0 here. So it may be in between that. So 3, it's not actually 3, not 9 omega h, it is currently not, so it may be 6 or 4. Let us check. So let us check which out of 6 and 4 which is maximal, then we actually done. So let's check that. So up to now what we have argued, that since the minimum energy in that system, that means 3 staircase and 3 individual, the minimum energy will be 3 omega h. 3 omega h, 3 wh, since minimum energy means, that means I put all the 3 individuals there, so 3 I will get 3 omega h, there is no other way. So here it is entropy 0, the maximum energy will be, I put all the individual here, that means that way I'll get the maximum energy 3 into 3 wh, that is actually 9 omega h. And since it is the only one possible way, so that means here also the entropy is 0. That means first two option, that is 3 wh and 9 wh, is actually wrong. So we have to check the how many possible ways I can put, how many possible ways and I can get 6 omega h and 4 omega h in the system. So let us calculate that. So I have this system w, so this system, one with omega h, wh, 2 wh, and one is 3 wh. So 6 energy how can we get? So first if we put one individual there, so I'll get total energy 6 omega h. I can put 0 individual here, 2 individual there, and 2 individual there. No, I will get no. So yes, 6. So I can put 3 individuals, 2 individuals also there, So, but one individual I have to put anywhere. So this is one possible ways, and there is other possible ways. 2 there, 1 there, it is not possible. 2 here, 2 here, 1 here, it is 5, it is not possible. 2 here, 1 is not possible. So it seems that it's only possible, means the only way is to get 6 omega h is also 1, that in only one ways I can get 6 omega h, that means the entropy will again 0. So that means I get the entropy for 8 omega h is also 0, 6 omega h is also 0, 3 omega h is also 0, 9 omega h is also 0. So remaining 4 omega h have to be the answer. So 4 omega h have to many possible ways, many, at least greater than 1. So let's check that. So 4, so omega h, 2 omega h, 3 omega h. Okay, now I can put one individual, 2 individual here, 1 individual there. I get 4 omega h. Omega h. So and another way, so 1 here, 2 there, it also greater than 1. So here on 1 here, so it will be 3. So it seems that with 4 also, with 4 omega h also 1 is actually possible, which is actually, if I put 2 individual there, 1 individual there and 0 individual there, then it will come 4 omega h. For 6 omega h I put here, here and here, so it is actually, the problem is, okay, the problem is I have not considered the indistinguishable argument here, so that's why it is coming all 0. So since indistinguishable, so I can put A here, B here and C here. I can also put, okay, so I think it is actually, I got it wrong from here actually. So 8 omega h, let me, in the first 8 omega h, okay, so in the problem actually it is actually wrong maybe, so let me do it again. Sorry guys, it is actually wrong. I haven't considered this indistinguishable property, that actually, that means that individuals are actually different, we can distinguish the different individuals, so we have to consider that factor also. So actually let go to the question 5 and calculate it again, then I will go toward question 6. So as we have discussed previously, the possible ways I can get 8 omega h is, if I put one individual in every staircase, will get 8 omega h, right? H 3h, no, 6h actually. If I put, okay, all right, let me write it. So if I admit, okay, if I put 2 individual in this energy level, okay, if I put one individual in the energy level, okay, let me do it again, then it will be very clear. I got it wrong. So the things I have taken for granted, that is the all individual are indistinguishable. That means if I interchange the position of these two individual, the configuration will remain same. It is actually true for the indistinguishable particle, but here the individuals are different, since in the question it is actually mentioning that the three individuals are different. So to it to let do it again. So here there is a three energy state. One is w, one is okay. One is omega h, one is 2 omega h, one is 3 omega h. Now if I put two individual there and one individual there, I'll get 1 omega h. But how many ways I can put two individual there and one individual there? Because I have three indistinguishable individual A, B, C, suppose. So that means I can put A here, B, C there, or I can put B there, A, C there, I can put A, C there, A, B there. So that means in three possible ways I can put there, right? So I can put A and B, C there, B and A, C there, C and A, B there. So now if one can say, now since they are indistinguishable, if I interchange B and C here, I will get another microstate. No, it is not possible, because in the state, if I interchange B and C, they will remain same, because it is does not matter where B and C remains. Means if the B and C remains in the two in the energy state 3 omega h, the microstate will remain same. So if one can say that if I interchange B and C, it may be it may create another microstate, but it is not true. Actually, if these two individuals are in the state 2, that is same. If I put B in the left or right, it doesn't matter. It's actually one microstate. So that means in the three ways I can I can put three individuals in the three state such that my total potential energy will be 8 omega h. So in the fifth questions, the answer will be 3. So answer will be 3. And in the sixth question, in the sixth question, let's see. And the sixth questions, the argument for the entropy will be 0 for 3 omega 3 wh and 9 wh remains same, because it's only one possible ways one can think, because if that's that there, and 9 omega 9 wh also there, so that is true. So these two cannot be the maximum occurrence, because the potential is 0. So microstate which in which we get the 3 omega h energy and 9 omega h, actually 1 and 1. So this is 1 and 1 now. So this is not actually maximum possible ways of occurrence. So let's see the how many ways 6 omega h can occur, right? So 6 omega h, how many ways 6 omega h can occur, right? Let's see that. So 6 omega h, so 6 omega h, number 6. So 6 omega h will be occur. So first will be omega h, second will be 2 omega h, third will be 3 omega h. So 6 can occur only, as I discussed previously, one particle here, one particle here, and one particle there. So this is the possible ways. So that means this is the only way. But since that the particles are indistinguishable, that means the possible ways will be A, B, C, C, A, B, and B, C, A. Is it A? Okay, let me write it properly. It should be 8 possible ways we can, maybe A, B, C, Okay, let me write it. How many ways I can put it there? It will be, let is A, C, B. Okay, now C, A, B. Okay, now C, B, A. Now B, C, A. Now CBA. So 2 4 another one will be, should be there. So 6 A B C. So if I interchange B C, A B C will be there. C, if I interchange A B, B A will be there. B A will be there. Now if I B okay, B, if I interchange AC. Okay, if I interchange these two, so this will be at BAC, right? So that many ways I can get AACC So is there any other possible ways? If I write it there, C in place of A, I can write only B and the C. So that is the only ways. Now one can say that another possibility is C in place of A, there will be B. So and if it B is there, so A will, so what B is there, so it's cannot possible. So in the 6, the total number of microstates will be 6. In the 6 numbers of ways we can possibly when the 6 is the 6 number of ways, we can actually get 6 WH energy from that system. So that means the microstate of the system will be 6. Microstate of the system will be 6 for the 6 omega h, right? And let's calculate the what is the microstate of the energy, the 4 omega h, right? 4 omega h, WH, 2H and 3H. As we have seen previously, it's actually if I put 2 individuals there, 1 individual here, only the case. So that means only the 4 omega is then possible, because 2 omega is from here and 2 WH from here, so 2 plus 2 is 4. Now how many ways we can write it here? Suppose that ABC we can write it here, ACB we can there, BCA we can there. So this you cannot write anyways. No, you can't write anyways other. So these only 3 possible ways one can get 4 omega h out of that system. That system is actually 3 individuals and 3 staircases there. So only the 3 possible ways to 3 possible ways to get the 4 omega h. So that means, so write it there. So that means one possible ways to get 3 omega h, one possible way is 9 omega h. So it is actually 6 possible ways to 6 omega h and 3 possible ways to get 4 omega h. So actually basically 3. So we can see that it is actually in the middle 6 omega h, it is right. 6 omega h is actually maximum. So that means it's actually symmetric. We can from here, means from here, and as we know that 3 4 between the 4 is actually, we also know that here. So it is that in the 6 omega h the entropy will be maximum. That means the entropy will be maximum as we are discussing, and if the entropy is maximum, that means it should tell me in that microstate the information will be minimum. Let's see that if I want to get 6 omega h energy out of the system, then that means we have to distribute the 3 individuals in what ways? In one individual here, one individual here, and one individual there. That means it is the maximum disorder state. In what sense? That if it is the possible ways to get 6 omega h, then means I cannot tell which individual is in which stairs in the maximal way. Suppose in another case, in the 4 omega h case, you can say that you can actually say by looking at the only 2 omega h that this individual is there. Suppose that a c individual is there, that you actually tell you that a b should be there omega h. So the information is there. But suppose that same case you actually observe that a is there, but actually then you don't know where this what is the which is the individual is to at the second stair and the which is the individual in the first stair. So here you actually know only by knowing only which is the individual which is actually there in 2h, you actually can say get the information what individual is there, what is the individual is there omega h. But here you cannot say exactly. That means this is the maximum, it is the maximum entropic state. That means in this state the information is less, the minimum information, the state, this microstate actually contain minimum information, because we cannot tell which individual is which there. But in the, as we are saying in the previously, that in case of Shannon entropy you can also see that that's in the case of Shannon entropy, if you plot the Shannon entropy, that is if it is 3 case, so if you plot the Shannon entropy it will get this type of curve and it will tell you, okay sorry, so if you Shannon entropy means P ln P, P is the probability of remaining in one state, so P ln P is the Shannon entropy. So in terms of Shannon entropy also, the one individuals remaining in one state is 1/3. That means it is the remaining one individual in any state is equal. So and you can check it from the Shannon entropy that it is the most the maximum position of the Shannon entropy also there where these p's will be uniform. Let it, if the p is uniform, that means it's actually 1/3 in case of 3 states, so p will be 1/3. If the uniform, this is the probability of remaining here and here is same, that means remaining any of the state will be 1/3. So that means if you calculate it here, so minus it will be 1/3 and ln 1/3, it will be like that summation of 1/3 ln 3 minus cancelled, so every is 3, so ln 3. So this will be the maximum entropy. So in terms of Shannon also, this actually says this configuration has the maximum entropy, and that means you can in combinatorial sense you maximally put individuals there. There will be maximum number of ways in which you can put individuals in these 3 steps here, where you will get the energy exactly 6 omega h. So the answer of the 6 will be this 6 omega h. The 6 omega h will be the maximum possible ways of occurrence. Okay, let me now let's go to the question number 7. Question number 7. Consider a staircase with 3 steps and 3 identical marbles arranged on them. The steps are of height h and the marbles are weight w. How many ways can potential energy be 6 Wh? Now here the catch is these marbles are identical, right? These marbles are identical. So how many ways you can get the potential energy? 3 steps, exactly 3 steps are there, and 3 steps are there. 3 steps are there and 3 identical marbles are there. So as we are saying here also, these are question number 7, h, wh, 2 wh and 3 wh. Now here the thing is these marbles are identical. that means you can't tell which marbles are which. That means you cannot distinguish which marbles are which. That means if you put, suppose that if you put here on one marble, here one marble, and here one marble, now you can tell that it is actually different if I swap these two marbles. If I swap these two marbles, by looking into it, I can't tell that these two microstars are different because they are identical. But in the previous case, if you notice that in the previous case here, if I swap two individuals, suppose that if I swap A and B, by looking into them I can tell that now this picture is actually different from the previous picture. Suppose that here and here I can swap these two individuals. I can swap this in two individuals and it will be C and B, but by looking into them I can tell that these two configurations are actually not same, because here is ABC and ACB. The thing is that B and C can be distinguishable, but in the case of identical marbles, this I can by seeing into them I can tell that that if I swap these two and two, what means if I swap these two, the two microstate will be remain same. I can't tell by seeing into them by taking a look into them, and these two microstates are different. So here, as we had discussed previously, let's see what is the possible ways I can put a particle such that I get exactly energy 6 Wh. So that will be let's calculate that. Let's see that. So if I put it here 6, right? So if I put it there, so it is 3 omega h, and if put it against there, so it will be 3 plus 3 plus 3 6. So it is one way, and is there another way. If I put it 2 there, 1 is there, so 4 5 h no. If I put 1 is there, so that's also not possible. So if I put 2 there, 6 omega h, but it is not. So now you can see that only one ways you can put 3 marbles into 3-step stair such that the total energy will be 6 Wh. So that means the case 7, in the case 7, how many ways can the potential energy be 6 Wh? It's only one. The catch is here, since these 3 particles are identical, that is why 1, and here the catch is 6, since these particles are indistinguishable, that is 6. Now why, one can say, why it is so that 6 for the 6 individuals it is distinguishable. So since I can see them and I can tell which individual which, that means that actually contains more information. That means that will be less that will be less entropic. But here, where these 3 are identical, but the information, I mean the entropy is the microstate is 1, that means entropy is 0, that entropy is minimum. Why it is so? Because here the uncertainty that I can tell, since there by looking into them, by looking into them, there is an uncertainty which individuals are where, right? Here, since they are distinguishable, that means the information is there, but I don't know. That is the fact. If I don't know which individual is in which states, that information I don't know. But here you say that question is not arise, because since they are identical, the question is actually not there. Which particle is in which staircase, the question is not arising. So that means here this actually if I know that, means since they are identical in identical sense, that means if I know that one particle is there in every staircase, I actually know everything about the system. There is nothing remaining to know about them. Since I cannot distinguish between these identical marbles, there will be no information needed for my purpose. But suppose in this case, suppose that I telling you that one individual which means one human beings are there in 3 steps here. That means then the question arises, one question arises, which individual is there in which staircase. So that means the in sense of information, I don't know which individual is there in which staircase. So that actually tells me that I need some information. The one individuals at every stair step is not enough to know about the whole system. I need to know that which individual is in which stage. So that's where that's it. That means the entropy, if I say that I will get 6 Wh energy if I put every single individual in every staircase, I will get 6 Wh energy. But if I do so, I lost the information which individual is in which stair. So that causes loss in information, and that actually means that it increases the entropy of the system. That's why in distinguishable in the distinguishable when different individuals case, the total number of microstate will be 6, and the entropy will be, if we calculate the entropy, that kln 6, so it will be kln 6. But in the identical case, since the identical case the question does not arises, I know actually everything. If I only say you that 3 identical particles are there in 3 identical particles are there in 3 steps here, all the things I need to know, I know. So that means here the entropy will be kbln1, which is actually 0. Is 0. Since I have told you, since I the nothing no means all the information that one actually know can be known by know that every one identical particle is there in one stair. That means no maximum information in my hand. So in that sense the entropy should be 0. So it is coming that mathematics tells me that entropy actually is 0. But in the case here, it says that it is a maximal means it is a minimum informal state. I don't know anything about the system here. So that intuition tells me mathematics should tell the definition of entropy should tell me that this state possesses maximum entropy. Now you can see the magic of this formula, or the way they have defined the entropy, that it is coming out that the entropy of this system, this situation, when the energy will be 6 Wh, will be maximized, which will be kln 6. So Rajesh, can you put Rajesh, can you mute your mic? Yeah, thank you, Rajesh. Sorry guys, there is a hello, can you hear my voice now? I have disconnected a few minutes back. Hello. Can you hear my voice? Hello. Yeah. Hello. Can you hear my voice? Okay, you can write it down there in the chat box. If you can't, well, okay. Let me see. Hello. Hello. Okay. Thank you. Yeah. So that's that. No, now let's move toward the next question. Since this is the definition wise, the entropy has succeeded its role to defining to capture the information in mathematical sense. So these examples actually indicating towards that. Now the question 8. Now the question 8 is an interesting question. So to move to the question 8, so we have to discuss some things which is actually temperature. So question 8: for system of marbles on an endless staircase, there can be cases of negative temperature. So it is the question asks that in the last example where the three identical marbles we put in the three staircase, it asks that if the number of staircase, a system of marbles, a finite marbles, it should be a finite marbles, not infinite marbles, it's finite marbles. If a system of finite marbles on an endless staircase, means in the previous system, if the staircase with the identical marble balls, if the staircase become infinite, is the temperature can become negative? It's a question. So what the temperature is actually? Now to going to that, we have to first define what is the temperature is. Now first thing we have to know about the temperature. Temperature is the property of the system which tells us its average energy. Its temperature is qualitatively related with the average energy of that system. Now to do the average system, now here the question arises that can I define the temperature of a microcanonical system? No, microcanonical system means if there is a system which is isolated from the which is thermodynamically isolated from the world, that means we cannot exchange energy with this system. Can I define the temperature of the system? Now the question is, since the temperature is actually telling something about the average energy of the system, that means if the energy of a system, microcanonical system, is remain same, there is no meaning arises of temperature, because there is no fluctuation of the energy is there. I mean, there is in that system, energy does not change with time, or energy does not actually changes, because it's an isolated system, microcanonical system, which energy does not changes with time. That means the question of average energy is not arises. So for microcanonical system, we actually not define the temperature. Now the case where if we allow energy change within a big reservoir whose temperature is T, which temperature again means that its temperature means its average energy, the reservoir's average energy is E. if we allow the energy exchange between these two system, this is my system and this is my reservoir. If I allow the energy change between these two reservoir and systems, then at the equilibrium, the system since energy is exchanged, the system's energy will be changes with time. Now in the equilibrium state, the temperature, that means average energy of the system, will be exactly equal to the T. That is we mean by the equilibrium, thermodynamic equilibrium, that when the system's average energy will be same as the average energy of the reservoir, that means the net ingoing energy from reservoir to system is exactly equal to the total energy outgoing from the system to reservoir. So then the average energy between us in a system will remain same, and the temperature of the system will be the temperature of the reservoir. So that's how we actually in first we define temperature. Now what is the connection between the temperature and entropy? Now entropy means the total number, in the some sense the total number of microstates, right? And the temperature means the average energy. Now as in the first question we discussed, if I have a microcanonical system, if it is a totally isolated system, it is not thermodynamically isolated but totally isolated system, that means the system's wall will be enclosed by the immovable insulated impermeable walls, then the entropy cannot change. But as soon as we couple the system with the reservoir, then its energy can change. If the energy can change, as we know that with the energy, as in the previous example we actually see that with the changing energy the total number of microstates is actually changing. Here also if I show you that in case of 6 omega is the total number of microstates is 6, and in case of 4 omega is the total number of microstates is 3. So that means with changing energy our total number of microstates is actually changing. So that means in principle there should be a connection between this energy and the entropy. Rather there should be, since the energy is fluctuating around, so we cannot connect this energy to absolute energy and the entropy. Rather we will connect the notion of average energy and the entropy. Now it is as since the system will always go towards a state, as the second law says that the system will go towards a state that will be maximally entropy, that poses the maximum entropy. That means it will reach towards the state where the system will have the maximum entropy. The system and reservoir, these will go towards a state where the entropy of these two total entropy of these two will go towards a state where the entropy will be maximum. That means the system will loses its information with time and it will go toward the maximum fuzzy state. Now since, and another word we know that since this actually so we know that the energy, the average energy in the equilibrium, the average energy should also be equilibrium with the reservoir. That means it should be connected by somehow. Now it is defined that the change of entropy with respect to its average energy is called the 1 by, is actually, it is defined in such a way. Okay, let me write it down. First we have argued that energy and entropy should have some role, because in equilibrium both energy is going toward the average energy of the reservoir and the energy of the reservoir, and the entropy actually goes towards its maximum position, and the average energy means the system's entropy, and the system's temperature will also in equilibrium will equal to T. That means in some sense in equilibrium the change of entropy and other terms, other macro state variables are remain constant. That means PV will remain constant. So that derivative of partial derivative of del S del E, the change of entropy with change of energy is actually 1 by temperature at the equilibrium. At the equilibrium, the slightest change in these the rate of change of this entropy with energy is actually temperature. You can see it also from this first and second law of thermodynamics. From here if we first law actually tells dq equal to du plus pdv, and the second law actually tell t ds actually dq actually if dq can be written as TdS equal to du, means is from the first law we get that, and from the second law we know that dq is actually can be written as TdS. So dq TdS du plus pdv. Now we can, from here you can see that is actually d not du, since I have written it's E, so it should be d of average energy, and you know that this average energy actually called U the internal energy of the gas. Now from here you actually know equivalence if you constant P, it's actually equilibrium, it's there is no equilibrium, no non-equilibrium things are going on in these two laws, first law of thermodynamics and second law of thermodynamics. In second law and first law actually tells about the equilibrium thermodynamics. So I got the first one, that at the equilibrium, and if I change with remaining constant every other things, that means if I constant P and V, that means if I constant V, this term will become 0, that means T ds will become d of average energy. So we can write it as del S, del average energy, is equal to 1 by T at equilibrium, and other thing is constant. So I get this formula from this laws also. These actually laws, you can't derive these laws. These laws actually coming from the observation. Now you actually again from these two laws in equilibrium, you actually again write a definition for this temperature through the entropy and average energy. Now you know what is the temperature and when one should add the temperature to a system, and from the intuition you actually get that things that the temperature and average energy and the entropy should be somehow connected, and we actually from the observation people wrote down two laws. That's actually nature's always follows. One is the first law of thermodynamics and second law of thermodynamics, and from these two laws you deduce another one things, that the definition of temperature in terms of entropy and average energy. So this is the things that there. Now one should always remember one thing, that this is actually definition, since these two laws are derived from the equilibrium StatMech or equilibrium thermodynamics. This is telling about the thermodynamics in equilibrium. So this relation actually holds in equilibrium, and from here also actually from the intuition we actually reach to the conclusion that at equilibrium entropy reaches maximizes, temperature become the temperature of the system will become the temperature of this reservoir, and the average energy of this say reservoir and the temperature will become same, and the the mean rate of going energy from the reservoir to system is exactly equal to, at equilibrium, exactly equal to the mean outgoing rate of energy from system to reservoir. From this argument we actually get the sense that there should be a connection, and from these two laws we actually deduce this the definition of temperature in terms of entropy and energy. Now last third question, question it asks, in the third question what it is asked, that consider a sphere thrips question 8, for a system of marbles, finite number of marbles,
According to textbook.
finite numbers of marbles, and if I put the finite numbers of marbles in a infinite staircase, can the temperature be negative? So to see these things exactly, you have to calculate the entropy, you have to solve these two equation, which is, since the finite numbers of marbles, that means if there are, suppose many stairs are possible, so if I put a number gi for representing, put I for indices for representing the ith stair, so that means if in the ith stair there are ni number of particles, ni numbers of identical marbles, that means summation of ni should be n, because a finite number of marbles are there, and if ni and I goes to 0, I goes to 1 to infinity, since infinite number of stair is there, so I equal to 1 to infinity, and in the second case the I equal to an energy, I equal to 1 to infinity. If it is remain in the ith stair, that means it will then have the energy epsilon I, and epsilon I will be I into h, because in the first stair its energy will be h, in the second stair 2h, in the third stair 3h, so ith stair it's IH. So we can write that IH, and ni number of particles is there, then it will be sum u, total energy, sum total energy E. Now to see exactly, you have to solve these two equations, in any of the programming language. So if you solve, that means since there are many variables and only two equations are there, there may be multiple solution possible, and every solution is exactly the microstate of this system. So that means these systems actually has multiple number of microstate. So to see the things that I am going to tell is the actually to check it in the computer by numerics, and in the numerics you actually put the only catches in the numerics there is no infinity, so you have to pick a large number for a large in compare if you put total n number of individuals, n number of marbles, total n number of individuals, then you have to put this summation, this infinity, which is suppose some number m, which will be much greater than m. In the computer you have to put this and you will get the exact result. But I will tell you from the argument why the temperature is negative or positive. Here the answer will be obvious. The temperature will is for a system of marbles on an endless staircase, there can be cases of negative temperature. False. Negative temperature cannot happen. So let's from this statement, let's argue that what is the negative temperature means. Negative temperature means that your partial derivative or derivative with respect to E will be negative number, some negative number, which will be negative energy. That means your entropy will be a decreasing function of energy. If it is a decreasing function of energy, then del E change the energy in a positive sense. If you change E to plus some number, positive number, S will become S minus some negative number, if the del S del E equal to minus negative, means that if I change energy by some positive number, entropy will decrease by some positive number, and this means this the entropy as a function of energy, will decrease with time. If or not time, if the entropy as a function of energy, if entropy decreases with energy, if I change positively entropy energy, then if the entropy change some positive number to some negative number, this is suppose that if I change it in the positive direction from here to here, some the entropy will decrease from here to here. So this will be S minus ds. So that means this curve actually poses that if the relation of entropy and energy will be that type of curve, then we can tell that this system has a negative energy. Now here we have infinite number of staircases and have a finite number of particles. Now how many ways we can put the particles to get maximum number of energy? So as the energy means, suppose that when the energy will become higher, I will the possible number of ways I can get that energy by putting the marbles on the stairs will become high, because the higher possibilities are there, because I have infinite number of staircases. That means I can put many particles in many ways that actually give me high possible energy. For us, suppose that if a finite, if in place of a infinite, a finite staircase is there. The infinite staircase, you will get only the maximum energy. Suppose that it is some m wh, this is energy, and that means you will get maximum energy 5 omega h. And how many possible ways you will get 5 omega h? Only one, because there are other no ways, because there is no other ways you can get the 5 omega h. So that means only one. That means in finite case, the maximum energy you will get where in maximum energy, the entropy will become 0. That means if the system the maximum possible energy is Emax for finite system, it should actually 0. But suppose here that in place of mh there is again one staircase above there. So if it is there, then means we can reshuffle it, and we can suppose that it is mh. So I put a particle there. So this is actually m plus 1 h. So I need some, okay, I put, suppose there is n, suppose again there my n particle is there. So maximum possible, the maximum possible numbers, possible energy mn particles are the infinite particle is there, mn into wh. Now this is mw is Emax is mn wh, right? Now suppose that I have another stair just above it. Now previously the only one, if this staircase is not there, only one way is there, that in the I get this maximum possible way. Now suppose that in case of that there is another staircase. Now is I can get m n w h in many ways. Let's see that. So if we put one individual there, so that means it will have m plus 1h, and other all individual there, other okay, so other is one particle and n minus 2 particle there, and other one particle here, right? So it's a m minus 1h, sorry, it's m minus 1h. So now if we add, there are n minus 2 particle here, 1 particle here, 1 particle here. If we add all of them up, m plus 1 plus n minus 2 m plus m minus 1 h, right? So h, so minus plus 1, so it is a 2m, so n, yeah, I get n minus 2 m plus 2m into h, so that means n minus n m h minus 2mh plus 2mh, so it cancel out. So I actually, so now that if only I add 1, I actually get one possible ways to one another possible ways to get the previous maximum energy, right? Previous maximum energy means that, so this is the, now it is not, the entropy of the system is not 0, but there are many other possibilities, but I can guarantee now that the entropy in this state is not actually 0. It is greater than 0, because one possibility is all the particle I put in the mth stair is one ways, and the second ways is I put one particle m plus 1 stair, one particle m minus 1 stair, and n minus 2 particle in m stair. So 2 ways I can, now in the morning many possibilities. Now you remember, now you just think about that, think about the definition of the infinity. Definition of the infinity means, if you assume some infinity is a number, if you take some number m, then your infinity should be larger than this number also. Whatever number you write m, your infinity should be larger. Your infinity is a number, your infinity is a number larger than that, right? Larger than that, what number you possibly think about. Now suppose you possibly think that I will think about some large number, and that means I can possibly, maybe I can, the maximum energy I can get out of it is maybe n m h, but since I have infinite staircase, that means there will be always another stair which is above from it, and that means it's guarantee, since I have infinite staircase, then there will be always a upper staircase. Since it is an infinite staircase, whatever number you think, and there will be always upper staircase, and if there is only, if there is uppercase present there, that means means the entropy of the system, since here that if one upper staircase present there, the entropy of the system cannot be 0. So for the infinite staircase, from the infinite staircase, it actually, from the definition of infinity, we actually get that there will be always one upper case above the whatever possible maximum energy you think about. That means your system's entropy will never become 0. And in the first case, as we seen that with increasing energy, with increasing energy the number of possible microstate also increases. That means number of entropies also increases, and it says that it's never becomes zero. That means these functions, that means that means my that means sorry that means these with energy the function of entropy will look like that. It will be monotonically increasing. It will be monotonically increasing. Since the entropy has no minimum, if it's since the entropy, if entropy become the daily del s daily means the slope of the entropy with respect to E become negative, that means it go towards the negative value of entropy, which is actually 0. But for the infinite staircase, for the definition of infinity, it is guaranteed that there will be always a upper staircase which increases the possible ways of numbers. That means it is guaranteed that for infinite energy case the minimum does not exist. That means the entropies, the del s del will E will never become negative. Del s del will never become negative. It always increases with energy, monotonically increases with energy. That means for the infinite staircase, the entropy, the del s del E will always become greater than 0, always be greater than 0. That means the entropy, definition of temperature is 1 by T is equal to del s del E will always greater than 0 for finite staircase. For infinite staircase. But you should always keep remember in your mind that for finite staircase, since in finite staircase there is possible there is a one possible maximum number, mth stair is finite mth stair is there, then the maximum stair you can think about is mth stair actually, and the possible maximum energy of the system poses is actually, if the n number is there, so n mh, and only one ways you can think about from how you, that's how you get this energy n mh. So that means in finite staircases the entropy always has a minimum, and it should look like, since it should look like this, and it will reach towards its minimum at some point, and actually this energy will be the nmh, and this will be the minimum state only achievable if the all particle in the minimum state, which will be nh. That means this energy will be nh for finite case. This will be for finite case, or for infinite case this minimum will not be present, because the concept of infinity, it always increases. That means always del s del t greater than 0, and you will have always positive energy. So that means the answer of my question is that how many answer of my question is for a system of marbles on an endless staircase, there can be cases of negative temperature? No, there cannot be negative temperature. If endless means if the infinite number of stair is there, then it is fine. So it is there. Now one can, what is the time now? Okay, now one can say that one can actually say that infinity does not exist in real life. Yeah, infinity does not exist in real life, but you can approximate it by saying that my m actually my total number of stair is much greater than n, then it approximately look like that. Means there will be a higher range of energy for which it will be monotonically increasing, and for that range my energy will be positive, and for other energy is not actually physically accessible. So in that range I cannot go physically, so in that range the entropy may become negative, but I can't go there physically. So in my physical regime where I can measure the temperature, it is will always remain always remain monotonically increasing and it always remain positive. So in natural, in physical scenario, you need that the staircase should always much greater than that the total number of individuals. So that is the today's class. If you have any question, you can ask now. Hello, is there any question, Rajesh? Otherwise I can end this meeting here. We will again meet at Saturday 4 p.m. next week. Okay, thank you for joining. I am ending this meeting now.